Hello and welcome. Today we have an interesting problem to work on. We're given a pattern and we need to show that that pattern does in fact continue, and we're going to prove that. So here's a pattern. First we notice that we've got a single number here, 1 squared, equivalent to 1 times 2 times 3 divided by 6. Now notice, this first number in the product matches this last number here in the sum. 1 squared plus 3 squared equals 3 times 4 times 5 over 6. This first number in the product matches this last number being squared here in the sum. 1 squared plus 3 squared plus 5 squared equals 5 times 6 times 7 divided by 6. This first number in the product matches this last number being squared here in the sum. So does this pattern continue? So we might imagine that the next piece of the pattern would have 1 squared plus 3 squared plus 5 squared plus 7 squared, adding up the squares of all the odd positive integers. And then that would be equal to 7 times 8 times 9 divided by 6, and so on. Well, let's find out. Let's first take a guess at what this pattern is, and then we'll use some mathematical induction to prove it. Here's our guess. We're summing up odd integers, successive odd integers, starting from 1. So 2i plus 1 is representative of an odd integer. Starting our counter at 0, we first get 2 times 0 plus 1 is 1. Then when I is 1, we get 2 times 1 plus 1 is 3. Then when I is 2, we get 2 times 2 plus 1 is 5, and so on. So we have 1 squared plus 3 squared plus 5 squared all the way up to n. And we're guessing that this is equivalent to, well, what do we see here? All these products are divided by 6. So we have 1/6 of some product. What is the product? It's a product of 3 numbers, the first of which is the last number being squared in the sum. So in this sum, the last number being squared, well, if we put n in here, we have 2n plus 1. So our counter down here will start at 2n plus 1. And then we subsequently multiply by one integer higher and another integer higher after that. So this 2n plus 1, we're going to have to count up to 2 higher than that, all the way up to 2n plus 3. And so we're multiplying these terms j, 2n plus 1 times 2n plus 2 times 2n plus 3. And then we're taking 1/6 of that. So here's our guess as to the pattern. Now can we prove this? How do we prove this by mathematical induction? Well, step number 1 is to look at the base case. On the left-hand side, with our counter at 0, we're going to add one term. So 2 times 0 plus 1 all squared. This is the first term of the series. What does that give us? 0 plus 1 is 1 squared, 1. On the right-hand side, we have this product dependent on n. Well, here we had our counter at 0, and that's as high as we went to, so you treat n as 0. So in this product, what we have is 1/6 of, well, 2 times 0 plus 1 is 1, and then 2 times 0 plus 2 is 2, and then 2 times 0 plus 3 is 3. This quantity in brackets is 6, divided by 6 is 1. So this checks out. Our base case works. Second, we're going to make our induction hypothesis. We will assume that if we take this series or sum all the way up to some value k, that it equals, well, when n goes to k here as well. So we get a sixth of the product of j going from 2k plus 1 all the way up to 2k plus 3. We'll assume that that is true for all values of k. Now we have our induction step. And so what do we have to prove in this step? What we have to prove is essentially taking what we have here and showing that for k plus 1, this equality holds. So we're looking at the sum as I goes from 0 to k plus 1 of this equals a sixth of the product of j going from, well, if k, we replace it by k plus 1, we get 2k plus 3. And if we replace k by k plus 1, we get 2k plus 5. So we're summing from 2k plus, or sorry, we're multiplying from 2k plus 3 up to 2k plus 5. Okay, so this is what we need to prove. So we'll go to our next board and see if we can prove that. Okay, here we are now back at our board. So let's go on with our proof. We had assumed true this statement. Now we need to prove this statement. Let's look at this left-hand side. The sum from 0 to k plus 1 of 2i plus 1 squared, we can write that as the sum from I going from 0 to k of 2i plus 1 squared plus, well, we didn't quite go all the way to k plus 1, so let's add in that term now. We get this. But here, the sum from 0 to k of 2i plus 1 squared, we had assumed true that that equals this. So we have 1/6 of the product of j going from 2k plus 1 up to 2k plus 3 of j, plus this. Well, here we're just summing up one term when I is k plus 1. So with I being k plus 1, we end up with that. Well, over here, we have three terms to multiply. 2k plus 1, then 2k plus 2, then 2k plus 3. Plus, and here we have 2k plus 2 plus 1, that's 2k plus 3. And now let's factor out a 1/6, 2k plus 3. When we do that, this term is left with 2k plus 1 times 2k plus 2. And this term here becomes 6 times 2k plus 3. Well, what we'll do in the square brackets is expand everything out. Here we have 2k times 2k, that's 4k squared. This times this is 4k, this times this is 2k, so that's 6k. 1 times 2 is 2. Here we have 12k. And here we have 18. And what we can do then is clean up what we have in this large bracket. So we'll move up here. And we end up with a sixth of 2k plus 3 times 4k squared plus 18k here plus 20 right there. Now what we'll do in that second bracket is factor out a 2. And now, from that second bracket, that is factorable. What we end up with is k plus 2 times 2k plus 5. This is a trinomial, quadratic. Product is 20, the sum is 9. So to get a product of 20 and a sum of 9, we can use 4 and 5. Break up this middle term, group pairs of terms, and factor. We'll get k plus 2 times 2k plus 5. Now, we're not going to reduce the 2 and the 6 because what we notice is if we distribute this 2 into this bracket right here, we get 2k plus 4. And having done that, what we have is a sixth of this times this times this. 3 successive integers. Well, another way to write that is to say that we're going from 2k plus 3 to 2k plus 5 in this product here. But that is precisely what we needed to prove right there. This is what we needed to prove. So this left-hand side, which we started with over here, is in fact this, which is the right-hand side. And there's our proof. Indeed, our pattern that we had originally does carry on indefinitely. And that's it. Thank you for watching.